All right, everyone, let's get started. Good afternoon. It's my pleasure today to welcome David Mortensen as our seminar speaker. David's a research professor at LTI at CMU. I'm sure most of you are familiar with LTI, the Language Technologies Institute at CMU. Yeah, and he graciously agreed to come on last minute to be here for us. Yeah, he got his PhD from UC Berkeley, and he describes himself as a linguist who does a lot of computational linguistics and NLP, and I'm really excited to hear what he's going to talk about today. So can everyone welcome David?
Hello, everybody. Today I'm going to talk to you about how extension is all you need, but sometimes good intentions help too. And I hope my clicker, oh, there it goes. Ah, not cooperating. Oh, oh, okay, that's why. Um, so if you're not familiar, intension versus extension is an important contrast in a lot of different fields. In mathematics, in philosophy, especially philosophy of language and semantics, but also in linguistics more generally. So intention is the definition of it's about defining concepts, formal definitions, like a formula. So for example, here on the left, we have the logistic function, and we have an intentional definition of it. Well, extension is about the manifestation of a concept in the world as a set. So on the right, we also have a depiction of the logistic function, but this time as a set of points, each of them representing a value, a coordinate that belongs to that function. But this is very, very abstract in a way. I'd like to talk about something more concrete. Who here has been to Switzerland? Who here has eaten Swiss food? So my wife is a Swiss. I for that reason go to Switzerland quite often, and I eat lots of Swiss food. And eating Swiss food, I've noticed a pattern. So if you take bread and you add cheese, then you get fondue. And if you take potatoes and you add cheese, you get a dish called raclette. And if you take potatoes and you add macaroni and you add cheese, you get a dish called Alba macaroni, which is sort of like the old OG macaroni and cheese. And this also holds for other Swiss foods like Haschnitte, which is basically cheesy bread, and Fashuchli, which is like quiche Lorraine, only with more cheese and spicier cheese. So the intention that we should assign to Swiss food seems obvious. A starch, something that is plus starch, combined with something that is plus cheese, yields Swiss food. However, consider the following. Suppose we take sticky rice and combine it with Kraft singles. We get what I call cheesy cow. Cheesy cow is not Swiss food, but Thai-American fusion cuisine. But we can fix our representation. We can fix our intention to rule it out. We can say that plus starch plus Swiss combined with plus cheese plus Swiss returns a dish that is Swiss. We just add the attribute Swiss to each ingredient. But what about Wurstsalat, sausage salad? This is also considered to be Swiss cuisine. Has anybody here had Wurstsalat before? It's not that great. So you take Wurst and you add cheese and you get Wurstsalat. This does not match the intention we have proposed. There are two solutions to this problem. We could constrain the extension and we can say Wurstsalat is not Swiss food, it's German food eaten by Swiss people. But to counter this, the Wurstsalat Weltmeisterschaft, the Wurstsalat World Championship, is in Sissa, in a town not far from where my wife grew up in Basel, Switzerland. You can also relax the intention. You can say that Wurst is a starch. In generative linguistics, this problem might be stated as all formal models both over and under generate. But the traditional formulation is all grammars leak. We'll refer to problems of this general type as the Wurstsalat problem. What is at stake here? Well, computational linguistics, in contradistinction to NLP, has tended to approach language intentionally, with significant exceptions, up to the current decade. My most cited publications actually belong to this tradition, and this kind of work is, if I may say so, amazingly fun and rewarding. But anchoring the computational study of language too tightly to discrete sets of formal definitions compels the computational linguist to ignore scientifically interesting phenomena. On the other hand, in practical problems, counterintuitively intentional approaches are sometimes helpful, even though NLP has been strongly extensional. So I'll present two studies. In the first of the two studies, we'll see that both approaches to the Wurstsalat problem, as it surfaces in natural language, are problematic. And in the second study, we'll see that an intentional model, like our model of Swiss cuisine, can be helpful in modeling language under some circumstances, but that modeling the set of dishes, the extension, directly is more generally helpful. So this will require a brief foray into the land of phonological distinctive features that for a few of you will be very familiar. So who here has heard of phonological distinctive features before? From like a linguistics class or what am I talking about here? Well, since Bloomfield and Jacobson, who were two 20th century linguists, then phonological intentions have often been expressed in terms of distinctive features. These could be acoustic or articulatory. The orthodox idea is that the difference between the S in English mace and the Z in English maze is solely that S is minus voice and Z is plus voice. So this feature, voice, one of roughly 20, binds together what is happening in the vocal tract, what is happening in the acoustic signal, and for Jacobson, but not Bloomfield, how the difference between S and Z are represented in the brain. So the structure of one of these features is sort of like this diagram here. The feature is the triplet that consists of a symbol plus voice, an articulatory expression like vocal folds starting to vibrate relatively early in a sound, and an acoustic correlate, high energy at the fundamental frequency starting early in a sound. So many linguists assume that the laws governing how sounds pattern in grammar follow this tripartite mapping. There have been dissidents, but this intentional view of distinctive features remains influential today in theoretical, descriptive, and computational linguistics. So one way of defining phonology intentionally is to say that phonology, the study of the sound patterns in language, is a system of statements expressed in terms of primitives like and including phonological distinctive features. So in the first study, we'll see that defining phonological intentions using phonological features to explain coordinate construction orders in Chinese, Lahu, and Hmong introduces a Wurstsalat problem. But an extensional approach avoids this problem and uncovers useful insights. And in the second study, we'll see that distinctive features can provide some useful benefits in practical NLP problems when a model needs to be language neutral. But otherwise, these purely extensional models seem to perform better. So the first study is joint work with Chen-Xuan Cui and Catherine Zhang. And it's about these kinds of these kinds of constructions called elaborate expressions and coordinate compounds. And these are basically words or phrases that are formed by combining two things that mean related things together at an equal level. So for example, to say a throng of people in Lahu, language of southern China, northern Thailand, and Laos, you say cha po, cha di, people pile, people lump. To say to learn to read and write or to become educated in Hmong, you say gun dao, to study cloth, study paper. And to say universe in Chinese, you can say tian di, meaning heaven, earth. So you combine two things together, and the meaning of the whole is sort of a generalization of the meaning of the parts. And they're at an equal level. So there's no inherent way, based on meaning, why universe in Chinese couldn't be di tian, but it's not. Why it couldn't be earth, heaven. And there's a reason, we'll see, why it's not. The ordering of these expressions, like which side comes first and which half comes first and which half comes second, appears to be ordered according to tone, rhyme, and tone, respectively. So, for example, in Hmong, so the consonants at the ends of the words, the M, B, M, V, actually indicate tone, like how the pitch of your voice is when you pronounce the word. So you can say gun dao, where the B tone comes before the V tone, but you can't say gun dao, where V comes before B. In fact, there seems to be, or was proposed to be, a kind of hierarchy that predicts, that you can apply to predict what order these things come in. Yes.
That like a second language speaker would screw up pretty easily.
Yes. As a second language speaker of Hmong, I screwed it up all the time, because when you're trying to make a new expression like this, it's very hard to remember, like, until you know the kind of rule. It's really hard to predict what order things will come in. The native speaker just does it without thinking about it, because they've learned the pattern, they've learned which words come first, which words come second, and so on. So across languages, we expect patterns like this with this negative prefix im or in or ing in English. We expect impossible, intolerant, and inglorious, where the little mn ingma, the nasal sound, is produced in the same part of the mouth as the following consonant. We do not expect the formally equivalent impossible, intolerant, or inglorious. And what a lot of people would say is this is because these patterns are based on these phonological features, these distinctive features that we've talked about. So, for example, in this case, you have a pattern that says neighboring segments should share certain features. However, when we look at this hierarchy that has been proposed for ordering these compounds in Hmong, we see that it kind of doesn't make any sense. It doesn't make any sense in terms of articulation or acoustics. So it goes from high falling to high to low creaky to low to rising to falling breathy to mid. It's like it's all over the place. And you might say, well, this is just some accidental fact or something that is fossilized, but I did a little two-participant study um, uh, and found that with made-up words, with nonce words, and I found that speakers use these wug words, these made-up words, or they order them in the same way that that roughly follows this hierarchy. So it looks like it's not just something that is fossilized or inherited in the language, but there actually is something, uh, um, as linguists would say, productive about it. So what about lahu? So lahu looks easier to rationalize. We can just say that words with high vowels come before mid vowels, which come before low vowels, and back vowels come before front vowels, which come before central vowels. This is perfectly easy to express in terms of these features. We can give it a perfectly nice intentional definition, except for one problem. The only problem is O, which occurs before everything else. It is phonetically a mid-vowel. So this is sort of nasty. Why is it doing that to us? What can we do about it? Well, we can just say that it's a super high vowel. It's analogous to saying that Wurst is a starch. But as we'll see, saying that this is not phonology is analogous to saying that Wurstsalat is not Swiss food. The phonological ordering effects present a Wurstsalat problem. If we approach the matter intentionally, then either the patterns are somehow not phonological, that we have to make these sort of bizarre exclusions, or the representations of phonological features do not mean what we usually assume they mean. So bizarre definitions. So we will, in a way, examine each of these options with some experiments.
Quick question before we get into the details of the development. Wouldn't you say the same issue with semantic ordering, for example, of adjectives?
With semantic ordering of adjectives, like in English, like the different, I would say, yeah, it doesn't necessarily follow from a general principle, at least as far as anybody, has convincingly been able to demonstrate. But, speakers of a language are very conscious, the fact that you say a good big brother, big good brother, that's not a good example, but that the big red house as opposed to the red big house. There's not a good intentional represent or rationale for why this is the case. But if you look at the data, then there is a strong tendency towards it being the case. Does that?
So the fact that it admits of some exceptions and doesn't line up with semantic, it's the same problem.
It's sort of the same problem.
Your philosophical issue here is not limited to phonology, is what I'm.
No, not at all. Not at all. Not at all. So let's get to some experiments. So our research questions are these: to what extent can the ordering of constituent words in EEs and CCs be learned by computational models? And what role do phonological representations play in this ordering effect? Our hypotheses are as follows. The ordering of Hmong and Lahu EEs and Chinese CCs can be predicted phonologically. These hierarchies can be learned by decision tree classifiers, and articulatory features will aid a classifier in learning to recognize correct coordinate constructions. So how we treated this just as a classification problem. So we have some elaborate expressions and coordinate compounds where the order is the same as in the data we found. And in some of them, we switched them. So we have A, B1, and B2 as attested, and A, B2, B1 as fake. So we have the labels attested and fake. And we filtered the data so that there were no instances, there were never more than one instance of B1, B2, because sometimes these pairs occur in different elaborate expressions. And we wanted to be sure that the models were not memorizing them. So we took and represented each of the onsets, rhymes, and tones of words in the different languages as one-hot vectors, and then concatenated them together. So for Hmong, that gave us 7 tones, 14 rhymes, 58 onsets times 3 words, A, B1 and B2, giving us 237 features. And we used 3 different kinds of classifiers. One was a decision tree, which provides good interpretability. One was an SVM, which we thought would help like model the interaction between features if more than one part of the word was relevant. And then rules, a simple classifier, rule-based classifier based on the rules that linguists had proposed. Here are the results. You see that for Hmong, the results are very good. In all cases, all languages, the random baseline is beaten by a long way. But in Hmong, you get all the way up to the 80s, even with duplicates removed. The rules, which are the green bars, actually perform pretty well. The determiner decision trees with only the features that the rules are paying attention to, only the focal features we call them, are almost as good as the rules. The SVMs are better. Even with only the focal features, the SVMs tend to be better than the decision tree, and even the rules. But if you include all of the features, then the SVMs are much better than everything else. So it appears that more than just the focal features are relevant, and having a classifier that can model these interactions really brings that out. So we also tried all of these conditions with phoneme vectors replaced by or concatenated with articulatory feature vectors. And in all cases, that just made it worse. That just confused the models. The learned trees, the trees that are learned by these decision trees, look remarkably like those proposed by linguists. So if you look at the one for Hmong, then it's almost the same except for one transposition. If you look at the one for Lahu, then it's the same except that there's some confusion here in the middle of the decision tree. It's rather hard to interpret. For Middle Chinese, that's what MC stands for. Then it's exactly the same. The learned hierarchy and the proposed hierarchy. So it looks like these do have to do with sound. Like sound is important to these, but it's like these articulatory features don't seem to be getting you anywhere. So the patterns were learned, largely learnable, based only on evidence from the pronunciation of the words. But it was never just one thing. It's never just tone, never just vowel, rhyme. For all languages, the SVM, which uses all syllable constituents, S features performs much better than the SVM that uses the constituent judged to be decisive by earlier linguists. You can see that in the table. In other words, phonologically, in terms of pronunciation, there are always multiple correlates of order. So it's like a particular case is not in or out. There are more or less prototypical first B1s and B2s, first word and second word patterns. So the order of Hmong and Lahu EEs and Chinese CCs can, in fact, be predicted phonologically, even with duplicates removed. And in Hmong, they can be predicted very well. The phonetically incoherent phonological hierarchies that predicted the order of EEs in Hmong and Lahu and CCs in Chinese actually predicted, in fact, well above 70% in all cases. And these hierarchies can be learned by decision tree classifiers. They learn strikingly similar hierarchies to what the linguists proposed. So it's awkward to say that Brusselat is not Swiss food. That is, that E and C ordering in Hmong, Lahu, and Chinese is not phonological. It clearly has something to do with sound, with pronunciation. But there's more to say. The patterns are not categorical, and the neat hierarchies perform less well than the holistic classifiers. So articulatory features as representations fail here. But so do these arbitrary hierarchies that linguists came up with. They're not capturing the whole picture. These ultimately fall short as well. So can models recognize EEs and their ordering patterns in context in a naturalistic corpus? From now on, because of the availability of data, we're just going to look at Hmong. And the hypothesis is that phonological information facilitates the recognition of correctly and incorrectly ordered Hmong EEs in context. So we set this up as a sequence labeling task and asked the model to assign BIO labels. So we have some of the elaborate expressions in the text that are in the real attested order. But some of them we switched. We switched B1 and B2 so that the ordering was wrong. And we labeled those as B and I fake. So we modeled this, we used 4 different approaches that were compared: a bi-LSTM, a CNN-based model, transformer. The results with the transformer were quite poor, so we didn't include them in the final paper. A simple baseline where we said that any ABAC 4-gram is an elaborate expression, and an improved baseline. This says see next slide. There is no next slide. But it basically took into account embeddings of the embeddings of the second and fourth word. So the goal here is to identify elaborate expressions and EEs and detect whether the order has been changed at the same time through this sequence labeling task. What do you think we found? Even the strong baseline was beaten by both the LSTM and the CNN. And by the CNN in the cases where we had the swapped tags, like I showed you. In fact, it doesn't degrade very much when we add the CNN's performance didn't degrade very much when we had added the swapped tags. So the in-context classification accuracy minus, so we actually filtered this data too, and to remove duplicates, but with duplicates not removed, then accuracy is like 99.5%. And phonological information doesn't help in any of the settings. Yes, Nate?
So the baseline was you added some additional embeddings in there?
Yeah, so we have basically we look at the cosine similarity between the embeddings of the second and fourth word, that is B1 and B2. And if it falls below a certain threshold, that is, if there's the semantic similarity between those two words is relatively low, then we mark it as not an elaborate expression. But if it's above that threshold, then we mark it as as being an elaborate expression. And we set that threshold empirically. So
That's just the word embeddings.
that's just the word embeddings trained on a 13 million word corpus of MAL. So we looked at the embeddings learned by these models, and they're kind of interesting. So if we look at a UMAP projection at the embeddings learned compared to a skipgram embeddings trained on the same corpus, we see that we see here words occurring first, that is B1, are shown in cyan. Words occurring second are shown in gold. And you notice a strong separation between the B1s and B2s, between the first word words and the second word words. In the tagger embeddings, there is a clear separation, but not in the skipgram embeddings. So the tagging model learns a lexical representation of B1 and B2 words that are different from one another, strikingly different, with no phonological information. The model learned that first position and second position words are first and second position words based on occurrence in the corpus. And there's different kinds of evidence that they had to learn this from. For example, many B1, B2 pairs occur independently as coordinate compounds, as CCs in MAL. And so it provides signal that the model can use to learn which is a B1 word and which is a B2 word. So in fact, phonological information does not facilitate the recognition of correct and incorrectly ordered Hmong EEs in context. So this lexical, contextual information is sufficient. In our third experiment, we used learned embeddings in classification. So we've got these phoneme embedding, or phoneme representations, where we concatenated the onset, rhyme, and tone one-hot vectors. And then we've got the learned embeddings from the tagger. So if we use these as features for a classifier, what is going to do best? And do either of them add extra information? Well, in fact, they both provide useful information. And the best classifier uses both the contextual representations and the phonological representations, not the phonological distinctive features, but just the phonemes, the onset, rhyme, tone. So bringing everything together, we have shown that there are two independent routes to arrive at the ordering effect: phonemes/tonemes and lexical distributions. Both contribute to the identification of incorrectly ordered EEs, but the information is not completely redundant. The unnatural phonological hierarchy is very robust, even though the learned embeddings provide much of the same information. So basically, if you just have tones, you're at 85% accuracy. All phonemes puts you at 88% accuracy, and phonemes plus these contextual lexical representations puts you at 93. So the conundrum is this: if we define a construct called phonology in terms of a coherent set of theoretic primitives like phonological distinctive features, EE and CC ordering cannot be phonology. We would have to stretch these definitions in totally bizarre ways. We have to say that Wurst is a starch. But if we say that these phenomena if we say that these phenomena are not phonology, we leave these patterns, which clearly involve speech sounds, without a home. It's not clear exactly what they are. And maybe it doesn't matter so much. Maybe having intentionally defined categories like phonology is less interesting than having extensionally defined categories like sound patterns. I'm going to skip this. So suppose that ordering started as a phenomenon motivated by intentionally coherent representations. Maybe this started out making sense in terms of distinctive features, but just has changed over time. So maybe to start off, voiced onsets. So we know actually that voiced onsets before were ordered before voiceless onsets, plus high tones before minus high tones, and then the tonal contours changed. This is common. And the ordering became a lexical pattern. So du always comes first, do always comes last. When did the pattern stop being phonological and start being lexical? At the first change in the tones? At some time later?
Sorry, can I ask what
Yes.
question that question is? I'm going to put Wittgenstein here.
Yes.
Let's say, maybe your philosophical question is just born of your desire as a human or a scientist to put labels on things. Why do we care which part of the linguistics department studies the phenomenon?
The point of my talk is that ultimately we don't. We should look at the phenomena as phenomena rather than trying to define, okay, this is what phonology is, this is what morphology is, this is what the lexicon is. We should look at it in terms of the extension of categories, or look at categories in terms of their not in terms of their definition, but in terms of their usefulness for talking about particular phenomena.
So to say you're going to break down the boundaries between different strata of linguistics or of language, do you have to switch to an extensional view? I mean, I'm thinking of like Jerry Stadock had a notion about autostratal linguistics, where the different things interacted with one another. The different levels of description interacted with one another to some extent, and were autonomous to some extent. But I think he was still intentional.
Yeah, I would agree, and I would say that what I'm saying is different from what Jerry Sadock was saying, which is that like the levels themselves and like defining levels ultimately is not ultimately just creates problems. Yes, we have to have labels, we have to have some kinds of categories, but I think it's useful to think about red. So what does red mean? So you might say that red refers to a particular span of wavelengths in visible light, or it refers to light that stimulates a particular kind of cone in the retina of the eye. You might try to give it a definition. But we learn less about language from saying, what kind of cone is stimulated by encounters with a particular kind of object than we just do by saying, okay, red is the set of things that are red, which sounds arbitrary, but it also gets you out of a lot of problems and allows you to talk about a lot of important things that would be difficult to discuss or would be made where bickering about definitions just makes things more difficult. So that's what I would say. So I'm saying, when I want to talk about sound patterns, I mean the set of things in the world that are sound patterns, in some sense, that we can recognize as of which that predicate is true, and not thinking too much about the formal definitions, concentrating on the phenomena as such and modeling them.
If I understand correctly, the way you're using, the way you're framing the issue, the job of machine learning is to take extensional data and create an intentional description.
That's true.
And
It's or to
your
take
argument
to take like extensional data and to yield discrete kinds of solutions in some sense, or yeah, but go ahead.
It's an intentional description. What I mean is it would generalize to new examples.
Right.
And I think your perspective, which I totally agree with, is that we shouldn't assume that those intentional descriptions are going to have some nice interpretable structure.
Right.
So when you're saying you focus on the extensional thing, you're saying let the data speak,
Right.
not that the thing that it speaks shouldn't generalize.
That's correct.
That's
correct. Yes. Yeah. And in fact, in interest of generality, we have these this note here. So the question is that we if we tie ourselves in knots trying to sort out definitions in an intentional sort of way, we sometimes miss what is actually happening. And here's what I think actually happened with Hmong elaborate expressions. So we started off with phonotactically based ordering. These words, originally coordinate compounds, were ordered to avoid certain combinations of sounds. And these were things that could be defined in terms of, to which we could give a definition. But then tonogenesis happened. And what this means is that some consonants became tones. So you end up with tonally based ordering from that. Then you have other patterns that speakers latch onto, particularly in cases where the tone of the two words is the same, so it's on the same part of the hierarchy. And so these patterns end up getting propagated through in speaker behavior. So you end up with tonal / segmental ordering. And these patterns get generalized. But the tones don't stick around. The tones change. The contours of the tones, like what the larynx is doing when it's producing a word, it changes around without really changing the categories. So something that had one tone, all of the things that had this A2 tone in Proto-Western Hmongic would have a falling tone in Tananshan and a high falling tone in Hmongleng. And these are not the same, but they are the same category, basically. So you have these tone contour changes, and you end up with arbitrary tonal segmental ordering. And then you generalize the lexical patterns, and you end up with this mixed lexical phonological ordering, which is what we see now. And if we concentrate on whether a pattern is phonological or whether it's lexical, or whether it's something else, we can kind of miss the fact that there's this very nice story about how you got this particular phenomena. That starts off with something you could describe intentionally, but ends up being something where intentional descriptions are not very useful. So you don't really gain anything by modeling coordinate construction ordering in Hmong, Chinese, and Latin Lahu intentionally. But if you model it extensionally, if you let the data speak, if you look at it from this perspective, then there are useful insights. So I'd like to stop there and ask if there are any questions. Yes.
Naive question, but why do we think this starts out being a phonological phenomenon and then lexical things came about, not the other way around?
So a good question, and it's a historical linguistics question. So the categories that govern that tell you where on the hierarchy you are can be traced back to phonological patterns that are known to have existed at an earlier stage in the language. So that's why we think that, or I think that, the phonology was first, and it fed these lexical tendencies that got generalized in different kinds of ways. So that's why I would say that that is the case.
Is that true of coordinate constructions throughout different languages, or this is specific?
No, it's specific to these languages. There are cases, like in English, we have coordinate constructions, and there are tendencies in their ordering, and they don't have anything to do with phonology as far as we can tell, except for very simple things like flip-flap, these so-called echo or duplication constructions. So, there's no reason to think that this is a universal or general, a linguistically general thing. Yeah. So I'm going to make this last part short because we are short on time. This is joint work with Willem Zohar, with Nate Robinson, who's here with us today, Nate Carlson, Calvin Chang, and Mrinmaya Sachin. So in contemporary NLP, words or tokens are typically represented as embeddings, whether that is pre-trained static embeddings, as a few years ago was the vogue, or embeddings that are learned via backpropagation in the training of a neural network. These embeddings usually have a semantic goal. Tokens with similar embeddings should have similar semantics in some sense. Tokens with maximally distant embeddings should be unrelated in meaning. But some tasks need phonological, not merely semantic representations, like cognate detection, loanword detection, key phrase extraction, cross-lingual NER, spelling correction, speech recognition. Not really speech recognition, but anyway. So here's how this works, or how this could work. So we have three words: soybean, ocean, and motion. And they're being fed into an embedding function. And we get back embeddings for each of these words, S, O, and M. If our embedding function is working, then O and M are going to be closer to one another than O and S. That is, O and M are going to have embeddings that are more similar to one another than O and S. So there's been various work in producing these kinds of embeddings, but until this study, there was no systematic way of evaluating or comparing phonetic embeddings. So we introduced an evaluation suite that measures how well they satisfy the basic desideratum, as well as proposing a few more approaches. So we'll look at the first of the phonetic embedding methods that have been proposed. And we'll do that briefly because we don't have a lot of time. Then we'll look at the evaluation tasks we proposed. And finally, we'll compare the performance of the methods on the tasks. So first, poetic sound similarity. In this approach, we map words to IPA, International Phonetic Alphabet, with the CMU Pronouncing Dictionary, map IPA to phonetic features, and then compute feature bigram counts, and represent these as a fixed dimensional vector, and then reduce the dimensionality with PCA. Note that this can be applied to words outside of the original training corpus because all that is learned is PCA. Then there's phoneme to vec. In this approach, you start with a gold phoneme sequence xi and a hypothesis sequence of phonemes yi. You represent them as phoneme indices encoded in matrices x and y of one-hot vectors. Then you read xi with an LSTM yielding a hidden state h0 and decode that hidden state h0 to y1 to yi using an LSTM and feature torsing. A phoneme embedding matrix is trained jointly with the model weights, and it becomes the encoding function. Phonetic similarity encodings proposed by Sharma, Dhawan, and Paila start with a sound similarity function. So you assume you have some function that can take two sounds and say whether they're similar, how similar they are. And you construct a matrix of similarity scores such that Sij is equal to the sound similarity of Wi, Wj. And then you use non-negative matrix factorization to learn the embedding matrix such that the loss in 4 is maintained. And the ith row of V, of course, contains the ith word from W. This cannot be used for embedding new words. You would have to recompute V. And out of necessity, we applied the English SPSE, the sound similarity function, to all languages because we had no way of recomputing it. So finally, count-based vectors as far as the simple things. These are the simplest. This is the simplest possible approach you could think of. This is a contribution of ours. So you just count symbol n-grams in the input. Use term frequency, inverse document frequency, a term frequency, inverse document frequency vectorizer of 1, 2, and 3 grams across the input sequence of symbols with a maximum of 300 features, which then become our vector embeddings, as you see in 5 and 6. Oh, there's also the autoencoder method. So we proposed using an LSTM autoencoder to learn a phonetic embedding function. So our remaining methods rely on phonological articulatory features and the notion of articulatory distance. So the assumptions are that each phoneme in a word can be represented as a fixed dimensional vector of ternary articulatory features. So words can be represented as matrices of features. And we can quantify how many features have to be changed or phonemes added, deleted in order to change a word X into a word X prime. The number of edits is approximately proportional to the phonological distance between X and X prime. The articulatory distance A induces a metric-like space structure on top of words in sigma prime. So it quantifies the phonetic similarity between pairs of words. So it captures this intuition that pat and bat are phonetically closer to one another than pat and hat, for example. So the first thing we tried along these lines was metric learning. We used LSTM to encode a sequence, giving us of graphemes or phonemes or feature vectors, which gave us a function f that maps a word to a vector h0. And then we train with a differentiable loss as shown in 10. So basically, this has the effect of forcing embeddings to be spaced the same way in articulatory space as A would space them. Similar to that, but somewhat different, is the triplet margin loss approach. So this relaxes the requirement that there be equal that spacing in the embedding space be exactly proportional to that in articulatory space. It just says that the same ordering should be preserved. We also looked at some semantic baselines. We looked at a number of different tasks for evaluation: replicating human similarity judgments, replicating articulatory distance, retrieving the most similar word, completing sound analogies, recognizing rhymes, identifying cognates. We use data from Amharic and Bengali in non-Roman scripts, English, French, German, Polish, Spanish, Swahili, and Uzbek, also in a non-Roman script. Here are the results. And here are the winners. So you'll see that our approaches performed better on the whole than the other approaches. And in particular, triplet margin loss performed well. Note that here are the approaches that used intentional supervision. And they seem to do quite well. In fact, the overall winner is triplet margin loss. However, if we look at the tasks that were defined in terms of articulatory space, A, and those that were defined independently, we note that triplet margin loss is the winner only when the task is defined in terms of A, times defined in terms of articulatory space with the intentional representations. In a lot of cases, in two cases, the best performer is actually the count-based vectors, the simplest approach, which is purely data-driven, with no intentional representations. So to close, it's not without reason that NLP has gone from building formal representations, modeling language from the inside out, to modeling data, modeling the surface language in terms of surface distributions. The former sort of sentences the language technologists to the hell of the Wurst-Salat problem, and the latter provides a way out. However, if you only have access to a small sample of an extension of a concept, intentional representations can be helpful. They're also fun, and I like them, but extensional approaches are fun too. Questions? Nate?
If you could try a new way to do chronological embeddings, be applicable to a wide range of tasks, just given things you've seen since this project has done.
Well, I have always held out hope that using a transformer language model over phonetic transcriptions or over some kind of phonetic symbols could perform better, could learn better embeddings than these other approaches. But I don't know. We've tried some things like that and we could never get it to work. So maybe it doesn't work. But intuitively, I feel like something along those lines should work. So you should be able to treat learning these embeddings as a side effect of a language modeling task. Anyway, nothing new. You already knew that.
No, I hadn't really thought about it in that way before. I feel like one issue with just like phone characters IPA is that P and P are just as good as each other. Maybe you could do sort of a byte T5 inspired thing where the phones themselves would be the articulatory features for like a sequence of 1s and 0s.
Yeah, I think that is in some ways equivalent to. Now that would be interesting to try. Yeah.
We have time for about one more question. There's not any.
Any questions? We can go early.
Yeah, normally people about 1 o'clock for rounds like these.
Yeah. I didn't intend to go so long, but there were earlier questions. So
Well, with that, let's thank the speaker again.